talking about how energy flows in the biosphere today. One topic that we'll start with is actually what someone asked about during the daily review. It's an idea called albedo. And so I'll give you the definition of what albedo is. Albedo describes how much energy is reflected. And the opposite of albedo is insolation. And notice how I spelled it. That's not me not knowing how to spell. I'm not saying insulation, like the pink stuff that's in the walls of your house. I'm saying insolation on purpose. Now, if any of you have ever learned a little bit of French, you might know that the word for sun in French is soleil, and it comes from the root in another language. So S-O-L, when it's part of a word, is referring to the sun. And so the opposite of energy being reflected is called insolation. That's how much solar energy is absorbed. So I tend to use the word albedo the most, but just because every once in a while in a question we might use the word insolation, I want you to know that that's what it means. So we said that the lithosphere can sometimes absorb and sometimes reflect the sun's energy. And so what gives something a high albedo? Things that are light in color and things that are shiny in texture. So if I were to ask myself, what's an example of something that's light colored or that has a shiny texture? I would think about ice and snow. Ice and snow are white, they are shiny. Ice and snow have a very high albedo. So the picture to the right illustrates this idea first. One side has no snow or ice cover. So it's just like a mountain, a hill with some grass and some trees and some flowing water. The other side is covered with ice and with snow. And if you look at the arrows that are coming from the sun and then bouncing back, you'll notice that on the field on the left, this arrow showing what is being absorbed is quite thick. That means the side on the left is absorbing a lot of the sun's energy. On the right, notice how the thick arrow is the one that bounces back. This is trying to describe that in that case, we're going to reflect a lot of the energy that came in from the sun. So even though the sun is shining on both spots, the side that has more snow and more ice will reflect away more of the sun's energy. Less of it will be absorbed. So what does this mean overall? This means that polar regions receive less light and reflect more. So it's a double whammy. Not only is the sun not shining directly because of the angle of incidence, but the sun that is shining, a lot of it is being reflected because a lot of the polar areas are covered with snow and ice, which would have a really high albedo. Now, what does this mean for living organisms? You'll see on this picture on this side, I drew a bird. I didn't draw one. I found a picture on the internet and pasted it here. And here's the reason why. When an area absorbs more of the sun's energy, it creates thermals. That's rising air currents created by warmer, less dense air. So here's what we're saying. What happens on the lithosphere affects the atmosphere. And then we'll see that what happens in the atmosphere affects the hydrosphere. What happens in the hydrosphere affects the lithosphere. They all affect each other. So because on the side that has less snow and ice cover, more of the sun's energy was absorbed, that means that air on that side will be warmer. This is especially helpful for birds, like big predator birds, birds of prey. You can often find them flying or probably gliding over or in these thermals because the air that's warm and rising keeps them aloft, which means in the air, with very little wing flapping on the part of the bird. So birds don't know science, but birds can tell when it's easier to fly and not easier to fly, and they will gravitate towards areas where the air is warm and lifting so that they're brought up into the air without having to flap their wings. Now, would anybody like to ask any questions about the word albedo, perhaps, or about what's happening with these birds? So then at the bottom, I wrote the word clouds, and that's because I want you to understand that it's not only the lithosphere where we could describe albedo. Clouds are something that generally have a high albedo. In general, clouds reflect more of the sun's energy than they absorb. Now, saying something has a high albedo does not mean it absorbs nothing. It just means that it's reflecting more than it's absorbing. So these are relative terms, not absolute. So this and the slide that came before it about angles had to do with the sun's energy and where it's being reflected and where it's being absorbed, and how much we're getting in different places. What we'll start talking about next is what effect does this have on things like water and things like air. I see just one person still writing. There we go. So we are going to talk about the transfer of thermal energy. Now let's talk about the title first. Thermal energy is where we're talking about heat. And I just want to remind you what thermal energy really is. Thermal energy is due to the vibration of particles. So when something is hot, that means that the particles that make it up are moving or vibrating very quickly. And to transfer thermal energy, particles have to be able to come in contact with other particles so that they can transfer some of their energy. Because it's vibration of particles, what we're really getting at here is that particles have kinetic energy. They're moving. And when we measure heat and temperature, we're really measuring the average kinetic energy that particles have. So thermal energy is because particles are moving and vibrating. So there are a few ways that energy can be transferred. I wrote the word reminder because I taught junior high, and at some point in grade 8, you learn about conduction, convection, and radiation. And so I'm going to remind you what they are. Conduction is a way that you can transfer energy by two things directly touching each other. So for example, when I put a pot on a stove, I'm using conduction. Usually conduction is between things that are solid. And you'll see why. When things are not solid, when they're a liquid or a gas, we have a different word. The word is convection. Convection is how energy is transferred in a fluid, and a fluid is either a gas or a liquid. The definition of a fluid is something that can flow. A solid cannot flow. A liquid can flow, a gas can flow, but a solid cannot. And so we are really going to focus on convection, and that's because we're going to focus on currents, on water currents and wind currents, and how they transfer heat around the atmosphere, the hydrosphere, our planet in general. Now, radiation is the other way, and radiation is specifically for waves, not for particles. And so the only spot that we would really talk about radiation in this unit is when we are talking about the sun and how the sun's energy reaches Earth. That's the only spot where radiation is really playing a role. After that, we're really going to focus on convection. Now, does anyone want to ask questions about those three methods that energy can be transferred by? So you'll see that I've got a picture over here. I would not expect for you to memorize all of the ocean currents that exist in the world. That would be silly. What I want you to recognize is patterns that are happening. We are going to talk about wind, and we are going to talk about water. A current is a way to describe the path of moving air or moving water, as well as the energy that is going with it. Now, some of the currents are cold. Notice all of these spots that have a blue arrow. Those are cold currents. And if you look at what's happening, cold currents are generally going from somewhere that's polar, either at the top or at the bottom, towards the equator. And then warm currents are generally going the other way. They're going from somewhere near the equator towards somewhere that is polar. Now, is that 100% the truth? No, that's just the overall pattern that we see. What we're trying to get at, or we're trying to get you to recognize, is that the movement of water helps transfer heat. If I look at this picture, which is showing water currents, what it's showing me is that heat goes from equatorial to polar areas. And that makes sense. Areas near the equator, we know, have absorbed more solar energy. They have, if we talk about their energy budget, they have a surplus. They have more energy than really what they need, whereas polar regions have a deficit. And so currents are a way to help even out, not perfectly, but even out a little bit more the energy distribution. So what are currents doing? They are distributing energy. Now, since we've got oceans on this picture, I'll mention this now, but oceans are heat sinks. Oceans help store a lot of heat. Now, when we come back from Christmas break, we will spend quite a bit of time talking about water and all of the things that it does. But one thing I want you to recognize is that water stores heat. if you have ever noticed that even though, let's say Vancouver is not really at a different latitude than we are, it's not really that much closer to the equator, it is way nicer there. And one of the main reasons that it's way nicer, way warmer, is because they're close to the ocean and we're not. And the ocean is providing them with some additional heat that we are not getting because we are stuck in the middle of a bunch of land where there's no water to transport heat towards us. The other thing that I want to mention on this page is a little bit about ocean currents specifically. In terms of oceans and the currents that are in them, the movement in the oceans is due to a couple of things. One of the things that causes movement is wind. We know that wind blows all over the place, and because wind, we'll see, is based on difference in heat and difference in temperature, the movement of wind can help change the movement of water and water currents. The other thing that affects them is land masses. So if you look at the picture, obviously currents can't flow across land, and so their direction is guided by continents and pieces of land because currents will flow around them. Currents can also absorb heat from them. And just in general, heat. Anywhere that water is warmer or cooler causes vibration of particles to be different. Depending on how fast or how slow particles are moving, water currents will move slower or faster. Water that's warm and water that's cold will be at different depths. Does anyone want to ask any questions here about currents or specifically ocean currents? So ocean currents are one way that thermal energy is transferred. The other way is wind currents. So on this particular one, I have this beautiful diagram over here that talks about wind patterns. I do not need you to memorize every type of wind that exists, but to recognize the pattern. Some winds are called easterlies. Some winds are called westerlies. And I've got the picture up there so that I can show you the difference between them. Take a look here where it says easterlies and look at the direction that the arrow is pointing. It is not pointing east. It is coming from the east and going west. So easterlies originate east but flow west. Westerlies originate west but flow east. So if you've heard on the news ever, because we have this all the time, them talking about a strong westerly wind blowing past us, that's usually what's happening. That's wind that originates in the west and blows towards the east. Now generally, easterly winds are colder. And if you look at where they are, it makes sense. They're usually more near a polar region. Westerlies are warmer because they are closer to the equator than an easterly. And then finally, we have trade winds. Trade winds, if you look, are winds that are happening right at the equator. And what's really happening here, if I was to continue the arrows, is little circles. So trade winds are winds that are going around and around and around, but they line up right at the equator. And so trade winds flow between the equator and other areas, so we'll say higher latitudes, and this helps, just like ocean currents help, this helps transfer some of the energy, some of the additional energy that's being absorbed at equatorial latitudes to be transferred. Now, when we talk about wind in general, you need to recognize that hot air rises. That makes sense. That's how a hot air balloon works. You heat up the air, the balloon goes up. Now, this idea is what makes wind happen. How do I get hot air? The air could be heated by the lithosphere or the hydrosphere. So air that's over a mass of land that has absorbed a lot of heat, or air that is over a mass of water that has absorbed a lot of energy, will generally be warmer. Warm air rises. The other thing that you should know about air is that the direction that it moves in is based on temperature. So for example, wind will always go, so wind always goes based on pressure. And the idea is that high pressure comes from cold air. And so wind's movement is based on the temperature of the air. So the idea we're trying to get at here is that everything about wind is because of thermal energy transfer. If we did not have heat, wind would not even blow, and then once the wind is blowing, it can transfer heat from one spot of the globe to another. Would anybody like to ask any questions about wind here? So then the other thing that I want to mention is about weather systems. Weather systems, this would be where we're talking about high pressure systems and low pressure systems. But the idea is here that warmer air equals more convection. And the more convection there is, the more the weather will change. And so you might be aware, like here we have Chinooks, like it's really warm wind blowing through. But our weather changes like in a snap. And one of the reasons is because the wind has so much convection going on, it's bringing things quickly. And so the idea here is that more convection means faster changes in the conditions around us. So when we talk about wind, there's one more thing that I'd like to show you. But to do it, you're going to do a little demonstration so that you can see that it's actually happening. What you should have been observing is that your line was not straight. You were trying to make a straight line, but because your partner was turning the piece of paper in a circle, your line got deflected. It got bent. It got turned. What you were doing was illustrating the Coriolis effect. Now, what is the Coriolis effect? It is the rotational. Rotational means in a circle. The rotational movement of air masses and currents. So we're talking about wind, we're talking about water. So it's the rotational movement of air masses and currents on the Earth produced by the rotation of the Earth. So in our little example, the person with the pencil was the wind. And the person turning the paper was the Earth rotating in a circle. And because the Earth rotates on its axis all the time, wind doesn't go in a straight line. Wind goes in little rotations. And so we saw on both of the pictures, for water currents and for airflow, that air was always moving in little circles. It wasn't ever going in a straight line. It was curvy all the time. And this is because of the rotation of the Earth. Now here's something that's important for you to know. In the northern hemisphere, objects, so wind particles, water particles, deflect to the right. By that, we mean clockwise. The same way the hand of a clock moves, that is the direction that air and water circulate in the northern hemisphere. Clockwise looks like this. Now the opposite is true in the southern hemisphere. Objects deflect to the left, so this means counterclockwise. And counterclockwise looks like that. Another way you could think of this is that in the northern hemisphere, it's like we are tightening something, and in the southern hemisphere, it's like you're loosening something. Maybe some of you have heard righty-tighty, lefty-loosey for when you're screwing a screw or something like that in. The same idea applies here. So the northern hemisphere is like we're tightening a screw, and the southern hemisphere is like we're loosening one. But this is the Coriolis effect.